Hello. Okay. Yes. So welcome today. Good morning. We are going to talk about a very exciting topic today, right? We are going to talk about boosting, giving energy to the fluid. So let's see. Just before we go there, let's see. First, I had some comments on our last lecture. By the way, I got the feedback from some of you that our lecture that Salma had with you on the building the model, that was a bit fast, and also that you didn't get all the details. It was a bit too fast. So what I will recommend is that you can, whenever you have time, if you can go to the computer lab and you can work yourselves on the exercise, okay, with the exercise. I think the slides are very much detailed. They tell you all the steps you have to follow. But to get access, those of you who don't have access to this computer lab, you have to talk to Turi, okay, Ufslop. She's the one to give you access. Okay, but it's open. You can use it whenever it's not used by with class. You can use it, and just try it by yourself because it's quite straightforward. And especially if you have the slides. Okay? For those of you coming late, so here we have 3 things you have to take. Be careful, they are not stapled. So we have the exercise we have been solving in class. We have one of these methane chart, and then 2 of these pages from my compendium. Okay? Okay. So just before to close, last time what we have done, we said in a more general way, right? We have a reservoir model, a production model, and then we have to couple them. Okay, this one takes in charge of the depletion, recovery factor, saturations, how much oil I have left in the reservoir, and this guy takes care of how much I can produce. Okay, taking into account flowing flow line, flowing pipeline, and flowing wellbore. Okay, so we found we have to couple them somehow. There are different ways to couple depending how are the models. Then we talked about some comments about tubing size, and be aware this trend that you simply increase the size, the diameter of the tubing, and simply you get more and more rate. That's only valid for either single-phase liquid under saturated oil or for dry gas. Okay, when you have multi-phase, we will see, not now but later, we see that actually you have a change of trend. Okay, well, if you increase the size, you're getting maximum, and then after that you start going the other way. Okay, these are some trickiness of the multi-phase flow that we will cover later. Okay, then we talk about the value chain as something I have to make at each level somehow. Sometimes can be very simplified, sometimes can be very detailed. In this case we use like an average level of detail, and you have to use that basically to compute this economic indicator. Okay, that can be usually is the net present value, internal rate of return, break-even price, break-even time. You can use many things. Okay, we said what enters into each cost item. And then we say, how do we make our calculations? And from last class, I think, if you check, that's something I forgot, was my fault, sorry for that. But I should have given you this document. That is actually the problem we are describing, the field that we are going to solve. Okay, that's the one that you have, the first one there on the bunk. Okay, which is a snow white field that I have discussed it before. You have flow line, pipeline, separator, and then you have to do some things on this problem. Okay, we have already calculated the production profile. That's the compression part. That's what you're going to do. We're going to try to do together today. Okay. And here are the considerations to calculate revenue. Okay, we said we make a table Okay, we make a table per year and we start at the end of year 1. Okay, because we make some expenses in the first year and all of that goes at the end of the year. It's like an accountancy. It's a standard way of making accountancy, okay, making bookkeeping. So there I take all the expenses and all the revenue and I calculate the cash flow for that particular year. Okay? And I told you expenses, we had here the cost of drilling wells, we have the cost of the subsea system, and the cost of the subsea system had the pipeline, this long pipeline, 158 kilometers, and the umbilicals. We're going to see later what are the umbilicals, but basically all wells, they have valves, you have meters that you take the, for example, pressure measurement, temperature measurement, you have rate measurement, you have the actuator for the valves, you have the chemicals that you inject in the wellbore. So that those umbilicals are taking it from shore all the way to the wells, okay, to the way where they are injected. So that's the cost, and it says here paid, I think, year 1 and 2. I think that's also described in this document. Subsea manifold to be paid during the first year. The manifold, we didn't discuss it so much, but it's you know, the structure that houses all the wells, that you have 4 slots that you put on the seabed, and you use that as a structure to from where to drill the wells. Okay, in our simple sketch, it's simply this structure. Okay, it's a metal structure that where I have 4 slots. In the center I have the collecting structure called the manifold or the production header, and from there I connect the flow line to the pipeline entry module. We're going to see later you know, the layout, a bit more in detail, the layout of subsea systems. Okay, so we do that, calculate expenses. Here, please note we are saying the price of the drilling won't change that much every year in year 3, but usually there is some adjust due to inflation, okay, or due to new negotiation or something. Sometimes they freeze the price, they say we have to drill 8 wells, how much is going to cost each, and that price is going to be frozen in time. Okay, but usually we have some adjustment of this price that we have here, 100 million in this case, with time. Okay, but we are neglecting that complexity now. LNG plant, we are simply using a linear function. We know if we want to take more flow, then we have to make a bigger plant. Okay, and in reality, this is a very complex estimation of this cost. Okay, but we are saying simply using a linear function. But in reality, you change that rate. Well, I don't want to produce now 20 million, I want to produce 25, and you send it to the vendor, and the vendor has to spend like a month or 2 months just to give you this number, how much it will change. Okay, in our case, we are doing it in a course. We cannot wait these 2 months, or we don't have a company that will be willing to give us this number, so we simply said it's like a linear function. Okay. Yes, the LNG vessels, we didn't do it last time, we neglected, but we said each LNG can carry some amount of gas, okay, and can do 22 trips. So I simply, let me open the file. I think I did it after class last time. It, the NPV, and I hope you are, I here have the solved Excel sheet, okay, with everything that we have done in class, with all different approaches, estimation of plateau, now we will have compression. So I hope all of you, even I'm doing it for you in class, all of you are trying to reproduce these calculations, okay, these exercises. So vessels, I say the annual production, okay, how much I produce, and that has to be the maximum, because I have to have the number of vessels to take the maximum production. Later I can decide if to sell one of these vessels, if to rent one of these vessels, or to do something else, okay? But initially I need to process this, I need to transport this amount of gas, okay? So I say each vessel can carry this 86 million, right, and can make 22 trips every year. So I divide the amount of gas produced in a year by that amount, okay? And then I multiply times the number of, so this will be, this number alone will be the number of carriers, okay? The number of vessels that I need. Sorry, it's not this number, but it should be this number. Okay, so I need 386 carriers. That means I need 4, right? I cannot have 3.5 carrier. I cannot have 3.5 ship. I have to buy 4 ships. Okay, and after I have the cost of that ship, I simply multiply the number of ships times the cost of that ship. And then I'm saying that that number will be paid evenly during the first 2 years. So I have to divide by 2. Okay, 386 386 million each year, year 1, year 2. Sum all the expenses, sum all the revenue. Initially I don't have any revenue, but I start getting it from year 6. That was something also I forgot to show you last time, that we say we're making the assumption we start production in year 6. Okay. And then I sum all of this cash flow, and then I say if I want to sum this cash flow that were earned or were spent in different years, I have to discount it first. Okay, so to discount it I have to use this expression that I divide by 1 plus the interest rate to the power of the year, in which year I am. Okay, because the money I spend in year 1, year 2 doesn't have the same value as the money that I spend 10 years from now, or the money that I get 10 years from now. Okay. Then after that I have the NPV, and simply I see how the NPV is changing with this one will be just this one, the cash flow of year 1, but this one will be the cash flow discounted of the previous plus the current. Okay, and you see how NPV is changing with time. Okay, and at the end the final NPV, it's simply the last one, okay, when I abandon the field, which is at year 43 in this case. Okay, and we can make different plots, so that's the number I use to say my robustness. Then if it's very high, that number, I can see how robust that my project is. Okay, if it's very low, close to 0, that means it's not that robust. If it means that any change will make it be negative, okay, will make it to become negative. Some plots that we typically make are, so let's make here output to present NPV calculations. Graphically, okay, we typically have, for example, the cash flow. Okay, we can use, in this case, it's good to use $1 million, okay, because these numbers are big, versus time. And you see initially I'm just spending, everything will be a big expenditure, and then finally I start to get positive cash flow. Okay. Or you can also plot the cumulative NPV. What happens with NPV with time? Sorry, time here. Okay, remember NPV is just one number for the whole project, but in this case we say cumulative NPV. That means for every year I can have one NPV that is for year 1 will be just year 1, for year 2 will be year 1 and year 2, and so forth. Also in 1 million, okay, US dollars. And be careful, these dollars that I have here, they are on each year. Okay, the dollars that I plot here, they are on year 10, on year 20, on year 20, 14. Okay, but the dollars that I show here, they are all the same dollars of time 0, because that's what I did to be able to sum them. Okay, so be careful, these are different dollars. Okay, so let's put here okay, all of them are referred to time 0, while these guys, these US dollars, these are of each year. So it can be a misleading, because here you see, well, I have quite a high cash flow, right? But when I compound that to NPV, actually that doesn't represent that much because of the discount factor. I have that factor shrinks, okay, and we said maybe like half, maybe 1/3, it shrinks, okay. So, but the profile is actually quite similar. Okay, actually it doesn't go down, but this one goes down, but this one simply remains constant. Yeah, and it's increasing very slowly. So offshore projects typically have a very big dip in NPV initially, and then they start to become positive. Onshore projects, they are stretched a bit. They have less expenses initially, but then the revenue is not that, also is a bit delayed. Okay, so this is more like an onshore project, and this is more like an offshore. Okay, because we mentioned that in offshore we have to have all the infrastructure already built from the beginning. Okay, and in the onshore we can have less infrastructure, start producing. Maybe this one actually is not exactly like that, but actually I can get a healthy cash flow early. It's not delayed, okay. Something like this, okay, early. But then the earnings are not that much. It takes sometimes longer time to get the same earnings. Okay. Yes? You had a question?
I wanted to ask you, at time 0, you have NPV 0, NPV value of 0. Right?
Well, it really doesn't make sense to plot here 0. I should make it really with simply with year 1. Okay, it should start in year 1. Okay, but so it actually should start, if we want to, maybe you'll see the actual plot now because I have made it for you in Excel, but actually it should start here. Okay, and also this one starts someplace here. Okay, yep. So if for our case, okay, this point here, how do we call this point? When they have a change, a flip of the NPV between positive and negative? Break-even time? Okay, and simply that's also a number I use how robust is my project. If we will take 5 years, 8 years, 15 years, it tells you how much I have to wait to be making money on that project. Okay? But typically I use the NPV. So for the case that we were, I think I put it in the notes. We didn't do the plot. We were a bit running last class, but that's how the values that we found. Okay, investment is becoming very negative initially for -$4 billion, and then the NPV is slightly increasing and then becomes positive. Okay, and here it starts increasing very sharply, but then it's simply becoming flat. Okay, every time, because the production here is declining, so every time I'm making less and less revenue, I have also some operational expenditures, and when my NPV starts to go down, that's where I should stop. Okay? That's where I should say we abandon production. Okay, and that's the time where the revenue is equal to the operational expenditures. Okay, and in our case, this break-even time is between year 13 and year 14. But you have to do the plot. Okay, it's very fine, looks very obvious when I show it, but you have to make the plot and then see, aha, this is what Milan meant. Okay, because you can just say yes and you are a bit sleepy, but you know, by doing things is that not only I show you, but actually doing things is that you learn. Okay, in this case I have plotted this column, the NPV with time, and I have versus this column. But you can also plot the cash flow versus versus this column. Okay. What else did I have to say? Okay, so another thing is we always have to make, and the traditional way we take into account uncertainty is by using the principle ceteris paribus. Okay, the effect of uncertainty on the project is typically studied using ceteris paribus. Okay, and what that means is simply a fancy term to say one variable at a time. Okay, so that means one at a time. That means I keep everything else constant and I see the effect of one parameter. Okay, then I keep everything constant. So for example, we can have oil price uncertainty. Okay, we can have also cost uncertainty. Okay, the cost uncertainty for early phase is plus minus 40%, but by the time of the PDO, I try to reduce it plus minus 20%. Okay, that's for DG3. Okay, but DG1, DG2, that number is plus minus 40%. Okay, what other uncertainty could I have? Oil price, cost. Okay, volume, the N. Okay, and simply it's actually made in a very simplistic way. I have the base case NPV. Okay. Then I make almost like a table. I think we have that table here in our Excel sheet. Here to the right. Maybe you have it in the block 2. Yeah, in problem 1 you have it. So how does the table look like? You have oil price. Okay, and you have minimum and maximum, and you have the NPV of that minimum and the NPV of that maximum. You have also the original oil in place, or the Q. Okay, you have also NPV minimum, NPV maximum. You have the capex, for example, cost. You have NPV, also the NPV. So simply you are changing, because it takes so long time to change. If you change the oil price, it's not a big change, okay? Because it's simply you have take all the data that you have, the same production profile, everything, and you multiply by a higher price, okay? But initially the initial oil in place, that is a big thing. Okay, I have to change my models. I have to change reservoir model. I have a material balance model. I have to rerun production profiles. So really, actually getting these two numbers is a big engineering work. Okay, people are not going to be happy with you. Okay, And capex also, I simply can multiply the numbers, or can say will be pessimistic or more optimistic. It depends, but actually I can also work it with some sort of multiplier. Okay. And these results are presented, I think you have seen that before. It's called a tornado chart. Okay. In the x-axis I put the NPV, let's say $1 million, and here I put the value of the base, just to have a reference to see how we are. And then you say, what happens if I increase the oil price by 20%? I get a block like that. Okay, the price will increase up to here. So you say oil price plus 20%, oil price minus 20%. Okay, and here you have the value of the NPV. Okay, this NPV that I mentioned before on the table. You can also have the capex. The effect of the capex usually is a bit smaller than the price. Okay, for example, plus 20% in capex and minus 20% in capex. You have the effect of the N, for example, can be significant also. OIP, for example. So depending where is the zero, okay, if the zero, for example, is here, NPV 0, what can you say about this project? That is not so robust, right? Every small change, let's say there is a cost increase for some reason. There is this virus, you know, the guys fabricating, manufacturing the ship, okay, they are having delays maybe, and that will affect, maybe have an increase in 20%. The oil price, maybe something happens, it skyrockets up, or maybe it goes down. So you can have, if you have a small variation, you can very quickly change your project from profitable to non-profitable. Okay. While if your zero is someplace here, then you can say, well, only in the extreme, if something extreme happens, something, yeah, it should be the opposite, right? The capex here should be minus 20%, less cost, and here it should be plus, more costly. Okay. Yes? You're asleep. Okay? I'm also a bit asleep, I think. Okay? So if 0, for example, is here, you can see, well, it's farther away from the base, and really have to make a big change in the price and capex and to get to that point. Okay? So in that case, you say your project is more robust. We will see, and you have to make this chart in the exercise. Okay? You have to make this chart. But just I have to give the disclaimer that this is not a good way to evaluate uncertainty or quantify why? Because we are doing it one at a time, assuming everything else is constant. Okay? In reality, we could have all of these combinations happening. Maximum with minimum, minimum with maximum. We have many other things. So here, let's say the point is that we are neglecting other all combinations, okay? Other combinations. Okay. To do that, that's the topic we're going to take after boosting. That is, we're going to talk about probabilistic reserve estimation. We have to use sampling methods, and we use methods like Monte Carlo, Latin hypercube to try to quantify that that spread. Okay, and the way we do it simply is we try to make not a chart like that, but we try to make actually a chart that tells me probability here and NPV here, for example, and you try to make a chart that looks something like that. Okay, that tells you for my project I have, considering all uncertainties, all N, oil price, everything, I have this is the most likely value, and let's say 0 might be here. Okay, and I can see what are the chances or the probability that I will get a negative NPV. Okay, which is very similar to this plot if you think about it, right? But for making this plot, I only had to make 6 runs, okay, or 7 runs. 1, 2, 3, 4, 5, 6, 7. That's why the industry likes it, right? They just go and change one at the time, and they calculate these 7 values, okay, to make this chart. For this one, I maybe need more cases: 500, 200, a million, 1,000. Okay, depends how many variables we are using. That clear? This requires multiple. Okay, we are talking here in the hundreds, or in the 500s, or in the thousands, or sometimes 10,000s of evaluations. And that's why it's sometimes unfeasible because if we want to ask, for example, now we have a new plateau rate and we want to ask the cost, okay, then it will take a month. And if you calculate 1,000 by a month, each one will take a month. These are many months, okay? You say better not to develop any field. Okay, yeah, so before we go to boosting now, finally, I have used almost 40 minutes for this. Let's talk a bit about the exercise 1. Okay, the problem 1, I think you already have all the tools to solve this problem. Okay, it's very similar to the SNOVIT, but now it's in Tanzania. Anyone here from Tanzania? No? You're from Tanzania? Okay. Are you familiar with Block 2? This project?
I've been working in oil fields before.
Okay. But I think it's like it's a kind of popular, like it's in Tanzania, right? People, at least they know a bit about it. They know that.
I know where this. I know where this is. Yeah.
Okay.
Yeah.
Are you from Dar es Salaam? No.
No. Though most of my lifetime I've been there because of school, and but I'm originally from Mwanza.
Okay.
Yeah.
Yeah, I know. I had a student from Mwanza. Okay, so first it says you have to compute. The main objective is you have to have the number of whales and field plateau rate that give you maximum NPV. Okay. So for that you need, and you see everything that comes into calculating NPV. You need the rate per year, and for that you need the production profile. Okay, for that you need to make this calculation in time. Then you need the cost, which the equations are very similar. It's a field which is very similar to SNOVIT. So we are using similar cost equations, but the water depth is slightly more. Okay, it's like things like 1,500, something like that, or maybe 2,000 something. Okay, this is a very big uncertainty, right? Plus minus 1,500 meters. So I don't know who wrote this text. Okay, So you have to compute revenue, you have to compute cost, and then you have to see, then you have to make a change in number of wells, increasing or decreasing. You have to increase the plateau rate, increasing or decreasing, and see how your NPV changes. Okay? And then you have to take a decision. Yes? So it's very manual, but you're trying to find out by changing number of wells, it will give you longer plateau, or you can produce a higher plateau. You can get more revenue, but also will be more costly. Okay, so you have to see these two effects and see which one gives you highest NPV. Okay, and this is exactly what we discussed today, making a tornado chart. Now you want to see what are the effects if I have the gas price is plus minus 40%, the original gas in place is plus minus 20, and the cost is plus minus 40%. How will that affect your result? So you have to do exactly the same that I showed here in class. Okay, you have to make this chart, this simplified approach. Then there is a question that is actually happened for Tanzania. There was a big uncertainty. You see the way the subsea is, you have a lot of, actually you have these very deep valleys when you approach to the coast, and you have to pass through these valleys, so you have changes in the pipeline trajectory. Also here, so it was a big uncertainty to because the gas comes with some liquid, okay, just to see if you will be able to lift that liquid and take it to shore, okay, which is I forgot the name of the terminal of the area where they are going to build the LNG plant. So you want to see the effect that your pressure drop calculation, in our case we are using this simple equation, right, dry gas equation, from P separator to P plem, okay, this equation line. What happens if that equation is of plus minus 40%? Okay, if it's plus 40%, it should give you a higher pressure drop. Okay, if it's minus 40%, should give you less pressure drop. Okay, that will change the end of your plateau. So you see, really, if it's really worth making the investment for that, how much that change in plateau is going to affect your results. Okay, and that's exercise set 1. Okay, so the assistant is going to be giving, I think, the first session. Was it this week? You already had it or no? Yesterday? Okay. Okay, so you're going to work on that. You have a month to work on this project. The second problem is actually from also like a real field, which is in development currently. You have Altagota, who are 2 reservoir units, and the main idea here is to try to see how can you split production to maximize the plateau of the field. Okay, you have 2 units that are producing, and you have to have some field plateau rate. So you want to see how much to produce from each unit. Okay. And here, to make your life simple, we don't have equations because this is oil reservoir. So we are simply using this potential concept that we discussed in class. Okay, that simply tells you the maximum rate that the field can produce depending on the cumulative production. Okay, and you know how to make calculations, how to calculate profiles with this approach. Okay, I think we discussed it in the Snow White when we have done it. Okay, we solved that problem. Okay, maybe we did it here. Okay, I think it's here. Okay, we talk about this potential, right? The potential curve, and from there we found a way, different alternatives, how to compute the production rate. Okay, I think we had that in class. And I told you can also make an analytical development. So that's also something you might consider using. You have an analytical equation, so then you can say, I think how we have derived that equation was substituting it here, and then we did the integral, and then we found this equation. Okay, when the production potential is linear. So in that case, you have an equation. So you can do it either time by time, as we have discussed in class. I think it's before that we have done it here, time by time. Or you can also make an analytical expression for the field rate. Okay, I think. And the main thing here is that you have a big uncertainty in the initial oil in place. Okay, so you have to see how do you cope with that uncertainty. So that I leave to you. Okay, you have to find out how many cases you have to evaluate to, or how the splitting is changing with all the different in place. Okay, if I choose 45 or I use 150, how is the splitting changing to achieve maximum plateau duration? Okay. This problem is the production scheduling, like what we have done for Snøhvit, but for a saturated oil field. And I think you already have all the tools to solve it. It's essentially the same, but you have different IPR and different tubing TPR. And this problem 4, we are not able to solve it yet. This one we have to discuss maybe in not next week, but the week after. We have a short discussion on that. And problem 5 is actually related to the NPV. Okay, it's trying to find if you have an analytical expression of rate with time. And you have, sometimes you can make, it's not very common in the oil industry, but you can make continuous discounting. Okay, instead of making it every year, like you do here, and using this factor, you can use simply this exponential and the discount factor. So that gives you, if you do that, and that's the task, you have to calculate that analytical expression of NPV. You have an expression that you can use to study what happens if you increase the plateau rate, if you decrease the plateau rate, what happens if you change the interest rate, and what happens if you change the price of the oil. Okay? And I think the last problem, you don't have the tools to solve it yet. Okay? Should we take a break? Yeah? And then finally we go to boosting. Okay? Okay, let's take a 15 minutes break. Okay, so just to complete that discussion, typically the PDO, the Plan for Development and Operation, is not available to the public. Okay, we have some examples. I think is part of the material. You have the PDO of Visund, you have the PDO of Volve. Okay, but that document is typically not open to the public. Okay, but in Norway you have a summary that is sent to the parliament that has many elements of the PDO. Okay, and that one is public. You can find on the web. Bad thing is that everything is Norwegian, but you can see only from the pictures, you can see some nice and interesting things. Okay, they describe the field, the formation, what kind of fluids you have, the structure, how is it going to be developed, okay, the layout that they are going to use, and they have this part which is on the economic part. Okay, they use Bookmall, but I think they use Investeringar. That's Nynorsk, right? Okay, but this is exactly what we were discussing before. Okay, and you see you have Investeringar. That means the capex. Okay, you have plus minus variation 20%. Doesn't make that much change in my NPV. We have OPEX. Okay, where operational expenditures, then you have a bigger effect. for some reason. You have reserves, what we were saying, recoverable reserves. This will be equivalent also to oil in place, has a big effect. And then you see the price of the oil, okay, 7 to 110, okay, which was quite optimistic. Okay, they didn't think it will go down to 30, 40, okay, but it has a big effect, even getting it very close to zero. So that's what you have to make. Of course, we are doing it a bit simplified. We don't need someone to calculate the cost. We are doing that ourselves, but it's basically the same idea, such that you are aware of the things that we have to make when preparing the PDO. Okay, let me include that here. Okay, so now I think we should have a class exercise that I want you to work in groups. Okay, and you have to work on this part, that is that they are evaluating to use a subsea compressor, okay, which actually has two compressors in parallel, and you have a cooler. We will see now why you have a cooler, and we see now how the real compression station looks like. Okay, but basically they want to, and I think I have some nice images here, and that's actually something they are considering doing in the field, in the Snow White field. Okay, that's the plateau rate, okay, or equivalent to yearly gas production, and you want to keep it constant. So one part is coming from Snøhvit, the main formation. Then after some time they're going to put Askelat in operation, and then Albatros is also covering part of that. But after some time they need to use compression to simply maintain that plateau, and it's a significant part of the time. It's like half of the time they need to use compression. So you have to make those calculations to see how much I can get, what is the extension that I can get, and when I will have enter into decline. Okay. Okay, let's put that here as an example. So you're doing, in a way, a real case, of course using simplified data, but you're using like a real case. Okay, you know how to calculate up to here, and we have simplified producing from one reservoir unit, but now you see I'm going to use compression, and that will be at the plem. Okay, that will be here. Okay, so before I let you work on the exercise, first I want you to just make a backup. Let's consider a single well. Again, we had our choke, here we had a pipeline, and we had our separator. Okay, and I was plotting the P wellhead and the P discharge of the choke, okay, at a given time. So it was pressure, that was Q of the gas, right? And how will the PWH look like? How the curve looks like? Available pressure at the wellhead. You already forgot? Okay. If you forget, it's similar to, I have to go from PR, right, to PWF, that's the IPR. You always remember how the IPR looks like. And then, well, the pressure here will be like an IPR, but but shrinked. Okay, I will have less pressure available there. Okay, so the curve is like that. P wellhead available. Okay, and the required pressure I have here, how is that curve? Going up, right? Okay. Okay, P required. Okay. And when we are operating in plateau rate, right, let's say I want to produce this plateau, okay, what do I have to do? Usually I have this case, right, in plateau, during the plateau period. So what do I have to make? I have more energy, I have more pressure than what I actually need, right? So I have to bridge it. I have to take it down with the choke, right? Good. Now I told you with time what happens, which curve is affected usually. The available, right? The P wellhead is always going to be, for example, shrink and shrink. Delta P of the choke becomes smaller and smaller until I reach a point where it's something like that. Okay. So in choke, when I have a choke, when delta P of the choke is positive, okay, that means I can always, almost always find a way to bridge that energy. Okay, almost always. I can. It is always possible. So let's write it like that. To get, okay, or to achieve a delta P for a given rate. Okay. The main constraint there are a few things that we have to be careful. If the delta P is too big, right, what might happen? What kind of problems might I encounter if the delta P across the choke is too big? Okay. The velocities become, right, very, the critical. I have very high velocities in this throat, and I can have erosion. Okay, so I will have wear of the chokes very often. Okay, that might be a problem. Okay, I can have, so some problems are, I can have choke wear, or okay, choke wear. Okay, I can have, for example, I can have, for example, cooling, right? Because when I drop the pressure, we know if it's a gas, right, it's going to get very cold. Okay, and if it gets very cold, what happens? I can have hydrate formation. I can have simply the water can freeze in the choke. Okay, so I can have cooling, hydrate formation, hydrate or ice formation. Okay, choke wear. But these are not really big problems. If I have a big delta P, sometimes in onshore, what I can make, I can put two chokes, one after the other, and then I drop pressure in one and I drop the pressure in the next, two chokes in series. Okay, but it's something that I can solve. It's not something that really is going to stop me for getting that delta P. Now when I go to boosting, let's say I'm in the other case. Okay, let's say now my pressure, available pressure, is actually less than what I require. Okay, for example, I have, that's my available, and that's my required pressure, and now I am here. Let's say this is the Q plateau that I need. And you see, simply I can use the same approach like I did with the choke. I have this delta P, and this delta P has to be the delta P of the booster. Finish. Okay? Paper takes everything. I say, to deliver this rate, I need to deliver such a delta P. It's not so easy, right? It's not so simple. What are the constraints that I have that could affect that I don't get this delta P? What are some of the constraints that I have for a booster, a pump, some element that I put here to increase the pressure from this value that I have to the value that I need? So let's put here, with boosters, and this is a big difference with choke, with boosters, it is not always possible to achieve the desired delta P. Not always possible, okay? There means there comes a point where I won't be able to make that, to bridge that difference, okay? What are some of the problems we could have, or why are we not able to reach that delta P? Okay? Simply the equipment has okay, has a maximum delta P. Okay. Maybe I should move this down, right? I think here. Okay, the equipment has a maximum delta P specified. What are some of the other constraints? The power, right? We know that if I have, for example, the delta P is too large or the rate is too high, I need to use more power. Okay, what is the power expression for pumps, for example? You remember? You have to go now dig back. You saw it in kindergarten, the school teacher. What did they say? A school teacher told you, well, power of a pump, right? Of a pump, okay, is equal to rate times delta P, right? Divided by the hydraulic efficiency. Yes? That means that if my delta P is too high or my rate is too high, I'm going to have a big power of the pump. And this pump is attached to a motor. If I have this pump, okay, which I make with a symbol like that, typically it's attached to a motor. And this motor has a maximum power. Okay. And it's not in the oil industry, not simply I can put any motor that I want. Okay, I have some numbers that I use 1 megawatt, half a megawatt, but I can go up to some certain number. So if I say I need a 100 megawatt motor, you say you don't find that motor. Okay, even if you are Bill Gates, if you are the richest person in the world, you won't find a motor to give you that delta P. Okay, so that's one thing we have to be careful, that power constraints, because simply has a maximum power the motor, I won't be able to achieve that. What other constraint might I have? Okay, sometimes I have a minimum suction pressure. Okay, I need some minimum suction pressure at the inlet, okay, and that can be for sealing purposes, sealing of the machine. That can be for balancing loads, okay, loads on the impeller. All of you know how a compressor or pump looks like, right? No? Okay, well, I think I have some pictures, but it's not nice to show pictures. It's nice to be, okay? That's like a compressor looks like. It's not a good. I prefer to make the sketch. So you have, in the case if it's a radial pump, okay, or a radial compressor, the fluid is entering through here, and I have an impeller, which I didn't bring, okay, maybe I have in the compendium. Okay, maybe we use one of these guys, but then we have to close here, otherwise I'm going to be... Let's keep it here, balancing loads on the impeller, reducing loads on the bearings, okay? Because if you don't have this minimum pressure, you're not able to balance the loads, and then you're pushing the axis against this bearing, and it's going to get destroyed very quickly, okay? What other constraint do we have? We are forgetting something important. We typically have operational map, okay? That's what you're going to work with today. But we have for compressors and pump, we have some operational map of the equipment. We have some region of delta P versus rate that both pump and compressor are able to operate, okay, within that region. And simply you cannot go any place outside of that map, okay? I can change the model. I can use a different pump that has a different envelope, but I have to be always within that envelope, okay? Otherwise, bad things happen. And the last constraint we're going to look at here at least is outlet temperature. Okay, especially this is a constraint which is especially important for gas. Because if I increase too much, if T outlet is too high, then I can have damage of the sealings, okay, so deterioration of the seals, okay. I can have damage to the material, okay. Okay. Here also minimum suction pressure, we have a problem called cavitation. We're going to talk a bit later, okay. But these are essentially all the constraints we're going to be looking at in this course, okay? So simply it's not say, this Q, I need this delta P, finished. My life is happy. Okay, I have to take care of all of these things, okay? Usually with a booster. With pump, this is not so important. Yeah, with pump, this is not so important. But all the rest, you have to be sure that it falls into the map, operational map. You have to be sure you fulfill the power constraints. Okay? You have to be sure to provide a minimum suction pressure, and the equipment typically has a maximum delta P. Okay, so that restricts really the delta P versus Q that you have to find. So let's work now. You start to work on the exercise. And I will say the first step, try to team up in groups, okay, so you can have some discussion. But the first step, I will say, simply calculate the delta P and Q versus time. No looking at any constraint yet, as of yet. Okay. Be aware that you have now to change the equilibrium point. Okay. Until the end of the plateau, natural end of the plateau, we have made the equilibrium here, right? We calculate the available and the required. But now we are including this element here, and the choke is fully open. So now you have to move the equilibrium point from the choke to the compression station. Okay? And there you have to calculate available, if I have this 20 million rate, and required, and calculate this Q delta P. Okay? And after you do that, we are going to start looking at all the constraints. Okay? The file is on my website. it's here, and it's this Excel file, okay, and it should be the same that you have here. And I have added a column here to the right, columns here to the right, that they have everything we have done before up to plateau, during the plateau period, and from here we are starting with the compressor. Okay. Okay, so just work on that. Now we have to expand this, keeping this constant rate, but now making the equilibrium point at the compressor station, before the compressor station and after the compressor station. Okay, I call that P-plane required, and now P-plane available. Now this one will be the available pressure at the plane or at the suction of the compressor. Okay. So let's just calculate that first, and then we start to see how we put all the constraints, okay, in our sheet. It's more correct if we don't call it here plane required, but simply we call it compressor discharge, okay? Because it's not really in the plane. The plane is where I'm merging all the lines and they're entering into the compressor. And this point I have the discharge of the compressor. So you see, discharge pressure doesn't change, because on that line I always have the same rate and I always have again separator pressure. So that pressure remains constant. But the available pressure at the suction, which is this one, is going down with time, because reservoir pressure is going down with time. Okay? And the delta P of the compressor is here. Okay? So now let's go to our, now we said that's the first step, okay? We said we calculated these two guys with time. Okay? So now we want to see if we can produce with the compressor that this company provided, which is MAN, okay? If we can actually give that combination of rate and delta P, okay? With the power, all of these constraints. Okay? So let's look initially at the temperature. Okay? I think it's nice to start with temperature. For that we're going to use this chart. Okay? Initially I want to make it with the chart, and then we make it with the equation. Okay? So let me take let me just make a screenshot of the exercise here. What happens when I get all of these value errors? Simply it means no matter what pressure I put at the wellhead or at the PWF, PWH, I will never be able to produce this rate. Okay? Simply we need a negative pressure, which is not physically, doesn't exist. Okay? So I know that simply because of that, in these years from now on, I won't be able to produce this rate. Okay? It won't be physically possible. I have to reduce the rate. But at least for these 5, it looks promising. Okay? So let me just paste that here, that you have it on the notes. Okay, now let's see this diagram. Have you ever seen this diagram before? Pressure versus enthalpy. Also, maybe in kindergarten you saw it a long time ago, right? Okay, but this is for methane. Okay, which we assume our gas is actually quite close to methane. The molecular weight is 16, so it's actually we are using methane for our calculations. Okay, so this chart represents the behavior of the gas. So let's take one point, okay? Let's say year because we want something exciting, right? Let's take year, for example, 3. Okay, this 3 of compression. P1, how much is the P at the inlet of the compressor, or P inlet at that particular year? P inlet, it should be this one, right? 56.7. Is it? Yeah, okay. 56.7 bar. And what is the P discharge? 78 is constant, okay? 78.7 bar. And we need the inlet temperature. What is the inlet temperature? I think it's in the PDF document. Not this document, but this is here, I think. 67, okay? We know from the initial proposal they gave, we know we can have here a cooler, okay? So if the seabed temperature is 4 degrees and we have here 67, okay, we can actually reduce that temperature. It can be much lower, okay? But let's say initially we don't have this cooler. The cooler costs money. We want to save money to our manager, okay? We say we want to see if we can make it without the cooler, okay? So let's take 67. T in will be 67 Celsius. So how do I calculate T out of a compressor? You remember this obscure, a guy talking about compressor in your young years, in your young time when you were young? Okay. Let's do one thing. First, in this chart, let's first locate the inlet, okay? These two guys, 67 and 56. Can you do that on the paper? On the paper that you have? 56.7, how much is that in megapascal? Simply 5.67, right? Okay, so where is 5.67? Here we have 2, 3, 4, 5, 6, so it will be someplace here. Then I move all the way vertical line, horizontal line, right? And where are the temperature lines in this diagram? If you see very carefully, here we have temperature, right? So these lines that are drawn like this, these are the constant temperature lines. These guys here. This is at the tablet now is not cooperating, but actually these are the constant temperature lines. This graph is amazing, has a lot of information. We are not going to use the graph anymore for our calculations, but simply I think it's very nice to see graphically, you know, what happens. So let's see the temperature 67. Where are we? Where is that temperature? Here we have 50. Here we have 60, 70, 80, 90, and 100. Yes? Okay, so let's see, 67 will be someplace here. So this will be my T inlet. Yes? I cross with pressure, and I know the temperature lines are these crazy lines doing like an S shape. Okay, so I find the one that has 50, 60, 70, so it's between these two guys, and closer actually to 7. Mark it, okay, mark it on the paper. Now, I ask you, what is the most efficient way, if I was able to live in an ideal world, what is the most efficient way to compress that to 78.7? Where do we have 78.7? So here we have 7, here we have 8. 78 will be very close to here, right? Okay, so I have to take this point from this location to this pressure. Okay, a small increase. I have to take from this pressure and boost it up to that pressure. Okay, now what temperature should it have? higher. Okay, we have the impression if you compress gas or if you compress methane, it increases the temperature, right? So that means on the line that we have, it shouldn't go with the same line. It shouldn't go on this trajectory. We should go a bit to the right. Okay? Should be, because that's how the direction in which temperature is increasing. Okay? Now I ask you, what is the most efficient way, if I can say in an ideal world, to compress that gas from here to here? What is the most ideal way to do it? We have one parameter, right, that you forgot, was very obscure, you don't know what it's for, but it's called entropy, right? You remember that the teacher told you, if we want to make the ideal, no losses, no friction, no nothing, it's an isentropic process, right? The same entropy. You remember that from your teacher that told you? If not, I tell you, okay? That's the most efficient. If you were God, you can decide how to take this point from here to here. The best thing God can do, by nature, say isentropic. Nothing better than that, okay? And here in this chart is very nice. You also have entropy lines, okay? You see S, these are these lines that go in this direction. S equals 0, S equal 1, S equal 2, and so forth, okay? So we see for that point 1, what entropy do we have? Okay, is if you go on this line, right, is between -2, -1, so you have 1.2, 1.4, 1.6, 1.8, 1.9. Yeah, that's the entropy of that point. The entropy of 1 of inlet will be -1.9. What are the units of entropy? Kilojoule, kilogram, Kelvin. Okay? So I say, if I'm God, right? If I'm, which is a kind of a blasphemy, but if I can make the best way to compress this fluid here, it should follow this line. It should come from here to here, right? Ideally. Okay, and then what temperature do I have? Okay, then I end up here in this point, and the temperature of that point is T out, that I call it ideal, okay, and that is 50, 60, 70, 80, 90, right? 90 degrees Celsius. Okay, T out ideal is approximately 90 degrees Celsius. Okay. All of you found it? Found the point on the chart? No? Okay, we're going from here, right? You have the initial point, and you know the end point has to be in this horizontal line, okay? Because you want to reach to that pressure. I am telling you, if you don't know it from before, I'm telling you, the most efficient way, I cannot go against nature. The most efficient way is to go isentropic. Okay, so I move. The isoentropy lines are these lines that are shown here. You see S0, this will be -1, so this will be -2, -0.2, -0.4, -0.6, -0.8, -1. Okay? So I move on that line all the way here until I end up on that pressure. Okay? That's ideal. The best I can do to compress this gas from here to here is by following that line. Okay? Now, in reality, you know, it's not an ideal process, right? In reality, I have all of these friction losses, irreversibilities, etc. So in reality, my trajectory might be something like that. Okay? My temperature is much higher, will be much higher than the isentropic. Okay? So this I call it T out real. Okay, but before we do that, let's do one more thing. Also, again, one thing you learn in kinder, okay, in Barnehage, that was, we make a compressor, usually has something like that, inlet and outlet. Okay. And what happens if we apply an energy balance on this compressor? You remember the first law of thermodynamics for open systems? Okay, what we call the first law of thermodynamics for open systems. What did the law tell you? It tells you that the difference in heat, you have here heat coming in and out, right? And work also coming in and out, power. Q minus W will be equal to what? To the energy, mass flow that goes through the system, the energy at the inlet minus the energy at the outlet. Right? Okay? And also you know that this energy is made up of what? Here I don't want to screw up. What do you have in that energy? Okay, you have H, you have V squared 2G, and you have Z, right? That is E. Okay, and we actually neglect usually in a compressor or in a pump or in a element which is like confined to a place, we neglect these two guys, so we end up with this expression. In a compressor we don't have much heat coming out of the compressor, so we say this is equal to H inlet minus H outlet minus W. Okay? Yes? So it tells you that the power that you need to compress, this power is important for us. We want to know the size of the motor. Okay? We know we can only, I think there in the exercise, you see that the motor that we have is only 11 megawatts. Okay? So we are constrained by that power. We cannot put a compressor which is bigger than 11 megawatts. Okay? So how do I calculate that power? I need the mass flow, right? I need the enthalpy at the inlet, and I need the enthalpy at the outlet. Okay? Where do I get that enthalpy? From the chart. Okay? This chart is wonderful. It has everything we need. We have here enthalpy at the bottom. Okay? So let's calculate now. For the inlet, we have the enthalpy, right? For the outlet, we have the enthalpy, and we have the mass flow. We can calculate, ideally at least, how much that will require to compress from 1 to 2. Okay? To compress from inlet to outlet. So let's do it together. What is the enthalpy of the inlet? Okay, I simply come here on this line down, and that will be 50. Okay, 50 kilojoule kilogram Kelvin. H at the outlet, how much is that? Close to 100, I think. Sorry, it's not a kilogram Kelvin, but it's kilogram. Right? More or less. I think it's slightly less than 100, but might be 90 something. Do you read those values on your chart? This is assuming ideal, okay? We say here, that's the outlet, ideal. We know in reality we have the green process, but we are just computing for the ideal, okay? Ideal means is isentropic. Okay? So let's calculate here H inlet. So here we have 50 minus 100 and minus work, and we have, what is the mass flow? How do we calculate the mass flow? Mass flow is the Q standard conditions, right, times the density at standard conditions. Yes? And that rate, how much rate is passing through the compressor? The whole rate of the field, right? So this is 20 e to the 6 okay, standard cubic meter per day times what is the density of the fluid of this gas at standard conditions? I think for this we have to use the gas equation, P over density is equal to RT, right? And these T standard conditions. So density standard conditions is, and this R is the universal gas constant divided by the molecular weight. Okay, so I have P R T S C. Okay, how much is that? P standard conditions is already calculated? Oh, here, 0.67. Okay. Yeah, it's using the same equation. Okay. Good. Okay, so that is 0.67. So how much, what is the mass flow we have? Kilogram per cubic meter. So how many kilograms we have? (20 times 0.67) 13.4. Okay, that's how much is passing through the compressor in a day. Okay, 13 million kilograms of gas. Okay, a lot of people passing through this compressor. Okay. So, but here we have to be a bit careful with the units. This is kilojoule per kilogram, and I have to multiply times this 13.4 e to the 0.6 kilogram per day. Okay. But remember, we want this unit, we want it in watts or megawatts. Okay. So watts, what are watts? What are the units of watts? Joules per second, right? So I should change this guy from days to seconds. Okay, so I say 1 day is how many seconds? 24 times 3600, right? And how much is that? How many watts do I need for my compressor? Okay, so it's this guy times minus 50, okay, times divided by 24 times 3600 and multiplied by 1 million, right? I hope. 50, that's the delta P of the delta enthalpy. That's the rate in kilogram per day, and that's the change the conversion factor to change from day to seconds. Okay, and I get 7,754. Is that correct? Hmm? And that is in which units? 7 point. Yeah. Sorry for that. 7.7. That is megajoule, right? Per second, and that is megawatt. Okay. So this compressor, ideally, it will use 7.7 megawatts. Okay, to compress the gas from that pressure to the ideally. Okay, and you also see we get a positive sign for W, I think, right? 1500. Okay, so let's write that here. Ideal power required is 7.7 megawatts. Okay, yeah, more or less. Okay, so you see what this chart, we have used it to estimate outlet temperature ideal and also power required ideal. Okay, in reality the compressor doesn't use this path. Okay, it's impossible. Only God can achieve this path. Okay, in reality everything due to all this entropy, change in entropy, we have some part of the energy that is not completely converted to pressure, but it's actually converted to heat. Okay, when we compress, it's inefficient. Okay, so then we have, because we have the friction between molecules, we have all kind of effects. Actually, it's going to follow this path. Okay, where the temperature is much higher. To describe that path, we use what we call a polytropic process. Okay. So now let's use the equations. Okay, the equations are in this the part of my compendium that I gave you. Okay, this one. Okay, page 62, 63, equation 246. Okay, so equation 246 is what we use. We don't use the chart really. We use this equation, okay, to calculate the outlet temperature. And we say here the outlet temperature divided by the inlet temperature will be equal to P outlet divided by P inlet. This is what we call the pressure ratio to the power of n minus 1 divided by n. Okay, and this n is what we call the polytropic exponent, and that's something that you have to measure. The vendor of the compressor, they make a compressor and they measure how inefficient it is, how much it deviates, what is the path that it follows. Okay, polytropic exponent. Okay, that is the real compression, and the ideal compression is actually using, you can use the chart, but you can use also this equation. K minus 1 divided by K, and K is the ratio between this thermodynamic property, the specific heat at constant pressure, divided by a specific heat at constant volume. Okay, these are properties of the fluid. Okay, So if it's ideal, that means the violet process. Okay, I can use actually the equation with K, okay, to find that temperature. And if it's non-ideal, then the manufacturer has to give me with this N to calculate the end temperature. Okay? So let's maybe now do, I want you to make some calculation before we finish the class. So make that computation for the ideal, okay? Just for the ideal, and K, I think I give an expression for K, which is in page 64. Okay, it's in the footnotes, number 14. An empirical expression to estimate K is page 64, footnote number 14, 1.3 minus 0.31, the specific gravity of the gas minus 0.5. Okay, so just use that expression to see how much, from this equation, how much is the ideal temperature, okay, the isentropic temperature, discharge temperature. Be careful with the units, okay? To use that equation, always you have to use absolute units of temperature, okay? Always keep it in mind. You go to bed, you repeat it. For compressors, I always have to use the temperature in K, okay? Repeat it before you go to bed, when you wake up, when you shower, okay? Milan told me that I have to use units for these equations have to be in absolute. Okay, in Kelvin. Okay, otherwise, the difference will be big. Okay. That's ideal, okay? I'm going to put here ideal. Okay, you found the same number that I found? 93. Okay, I think you have on the exercise, I think there is you have a constraint on the outlet temperature, I think. The manufacturer usually the discharge temperature of the compressor has to be below 140 C to avoid problems in the seals of the compressor, avoid structural integrity issues in the pipeline, and avoid vaporization of the hydrate inhibitor. Okay? So because of the compressor, you have some seals that they are made of rubber. So if you go too high on the temperature, then you will have some problem. Okay? So we know ideally we just get to 93, but now we have to know for the non-ideal case, with this equation, right, with the n, with this n, we have to know how far in the chart we are going to go. Okay? If we are very inefficient, we can very quickly get to 140, okay, which is here. If we are very inefficient, then it will be like that. Or if we are very efficient, it will be closer and closer to this point. Okay. So the last task for this class, and then we finish, is to calculate this column, okay, T discharge. What is the temperature we're going to have at the discharge? Okay, for that you have to use the equation that I just showed you. Okay, this equation, and it's already programmed for you in Excel. So I think if you go to Alt F11, you should see it. Oh, it's actually not here. Yeah, we can make it, maybe make it very quickly. That is a function of T in, P, RP, pressure ratio, right, and N. And this T out will be T in times RP to the power of N divided over, sorry, to the power of N minus 1 divided by N. Okay.
It's better to add the 273 here.
Yeah. So here you can say T in inlet temperature to compressor in Celsius. Okay. And here we say T in will be equal to T in plus 273.15. Okay, and we can say here the T out that we obtain, we say T out minus 273.15, and here we say T out is outlet temperature of compressor in C. Okay, so we are converting what Peng said, very important. You do the conversion inside the function. Don't do it in the VBA. Don't do it in the in the Excel sheet. Okay, RP. Okay, I think I did it correct, I hope. If not, probably I will see the consequences. So first calculate the RP. That will be P outlet divided by P inlet. P inlet is this guy here. Pressure ratio initially is very small, but then it starts to increase. Okay. Now, how do I find the N? Do I have the N any place? Temperature of the suction is 67. Okay, that will be an input. Okay, how do I find the N? Okay, the N is something that the manufacturer has to give me. And in this case, if you check on the notes that I gave you, the manufacturer, they define something called polytropic efficiency. Okay, that is equation 247, page 63. Okay, so they define, if you have the K of the gas and you have the polytropic efficiency, that's something they do with measuring the compressor, they, you can calculate N, okay, from that equation. So in this case, the manufacturer has provided the polytropic efficiency, 0.7, and from there you have to calculate the N. Okay? And I think that there is an equation on the BBA to do that. And remember, this number is just describing the path, the real path of the compressor. It won't be ideal, but will be something else. The reason why they use the efficiency, this efficiency, is that this number can go between 0 and 1. Okay? While the N is a number that is, you don't know where it goes from, because it depends on the value of K. Okay, if it's 1.3, it will be higher than 0.3, 1.3, but can be 1.4, 1.6. So it's difficult for people to remember, you know. So if you define in terms of this polytropic efficiency, you know that number should always be between 0 and 1. Okay? So you see, polytropic exponent is simply taking equation 247 and clearing out the N. Okay? So you say polytropic, this is efficiency, okay, let's call it efficiency. This will be, we are going to assume is constant, which we are going to discuss a bit next class. It's not exactly like that. I don't know why I have this thing here. And the N will be this N exponent that is using K and is using NP. Okay, and you see the number should be higher than K, and in this case is 149. Temperature at the discharge is that equation that we just made, T out, and T out takes the inlet temperature, it takes the pressure ratio, and it takes that N, something happened. We have some hacker, Russian hacker, doing something here. Could you please, any of you has calculated these numbers? How much did you get for our no, but for our year, the year that we were looking at? I think it was this year.
105.
105. Okay. So if we go to our chart, just check in your charts that you have there. If we go to 105, okay, 105 is going to be a bit of a short guy, so you have to put it a bit lower. 100, 110, so it will be someplace here. That's the place where the point ends up, okay, this location. That clear? Yes? From there, you could simply go here, read the enthalpy, and then you can find the actual power that you need, okay, to compress these gas. Okay? Yeah. Next time, we're going to see, instead of going to this chart to read for the enthalpy, we're going to have an expression just to calculate this enthalpy, okay, such that you don't have to use the chart. Okay? But remember essentially what you're doing. You make a polytropic process representing your actual compressor, okay? And then with this endpoint, you have the enthalpy. And then from there, you can calculate the power that you need, that is actually needed. Okay? Yeah, any question before we close? Okay, try to make up to that point on the spreadsheet, okay, that we have done here. Because we are going to use it next Monday. We are going to continue the exercise looking at the next constraints. Okay, remember we have to go through all of these. Okay, we have still to check the power in a way that we can do it in Excel, not reading from the chart. This one, I think we have 10 bar in the exercise, that this pressure cannot go below 10 bar. And also we have to look at the map. Okay, that part will be a bit complex next month. Okay. Yes, so thank you for the session and see you on Monday. Okay, but please make complete the Excel file.